the crazy of getting the YouTube stream running for the first time and all of that. We know that some of you have kids at home, just a few maybe. We hope the Devops are replicating. We need more of us. And you may end up having to get to walk away, or you may just want to get to it a little bit later. So Paul, JJ, Laura, they've all worked really hard to put that together. So that said, we've got Thomas Ruble here to talk to us about how to build a quantum computer. So I want to go run and get my soldering iron while he gets ready to rock and roll. If you have questions, please write them out in the chat, and JJ will work to interrupt Thomas occasionally to field some of those questions. It gets a little difficult for him to talk through all of his slides and whatnot and pay attention to chat. So please be patient with us as we do our best to replicate an interactive environment. Thank you very much. And Thomas, take it away.
Here we go. All right, is this going through the screen right here?
Yes, it is.
Good, good. Thanks for verifying. First time for me trying to teach over Zoom. People do it all the time these days. It's good to see what it's like. Yeah, my name is Thomas Ruble. I'm an engineer at Google, software engineer. Not a hardware one. To make a quantum computer, I think a soldering iron and a freezer and a little bit of carbon will get you there. But tonight, we're going to talk not so much about the computers, but the computing. The goal with these slides is to build up an understanding of what quantum computing is, what it can do, and do this in the way that you teach programming with a hello world program. Rather than waving our arms and talking about what software does in the abstract, we want to quite tangibly and concretely go through a truly quantum algorithm, front to back, soup to nuts. I suppose this would be filed as a bit of an extracurricular topic for DevOps writ large. I think someday we'll be doing DevOps with quantum computers. In fact, it does seem like a reality. But that being said, thanks everyone for showing up. I'm glad that there's interest in this. And the reason we put this together is that quantum computing is coming, and I hope to help socialize the understanding of it and do what I can to facilitate with curiosity about this strange topic. That being said, please ask all the questions that come to your mind. We will stop and backtrack and open up space for talking about this as we go through these slides. It is not meant to be a soliloquy, but a dialogue. So as much as is possible with Zoom, let's try to turn that into one. Okay, in the chat on these slides, there's a link. You can take them, copy them, fork them, do whatever you want with them. These slides are out for the public. Please, if you find use in them, take them and have them. All right. Secondarily, I'll show the slide again at the end of this presentation, but if you can, we're going to have you, I suppose, scan this QR box with your phone, or if you go to the slides, you can follow this link to get feedback. That's really important, so we know how we're doing and can make these meetups valuable for everyone. Okay, so like I intimated at, we want to understand what quantum computing is without recourse to too many analogies or metaphors or pictures. And in order to do that, we'll talk about quantum computing through the lens of mathematics. And one of the surprising things about quantum mechanics is that it rests on very, very simple math. So we are going to dip our toes into just a little bit of algebra here or there. And the point of doing that is to make it more clear as to what's going on, to kind of whiff away all of the magic surrounding this and show that it rests on just a few principles. We're going to take that math and we're going to write some actual quantum algorithms using this circuit model that the world is slowly agreeing on is the best way to write algorithms. And as a grand finale, we will teleport a qubit. And it is as cool as it sounds. All right. Why are we here? Why is this interesting? Quantum computers can solve certain classes of problems tremendously faster than classical computers. The speed up is real, and we'll see a hint at that in here. And these speed ups largely can be categorized as simulation or optimization problems. For example, trying to simulate what a good capacitor would be for a battery, which involves understanding all these quantum mechanical interactions that go on in battery chemicals. And one of the most surefire ways to come up with the best battery is just to simulate all the possibilities. It turns out, even with the biggest supercomputer we can get our hands on, that problem is intractable. But quantum computers, since they are quantum, effects, we can leverage them to simulate what we want to see happen. And well, I think we all heard the big news last year that this isn't just a pipe dream anymore, that quantum computing might, I say that with emphasis, it might actually be realizable. They're getting better and better every day, and there's good reason to be optimistic that this is going to happen in 10, 20 years. Okay, here's our itinerary. Quick high level, we're going to talk about the classical bit, probably a bit of review. Then we're going to move into what a qubit is, and then talk about how we can arrange qubits in a circuit. Then we're going to get into what goes on with many qubits, which naturally leads us to this concept of entanglement, which will be really interesting. And then finally, we're going to use everything that we've learned to build up an algorithm for quantum teleportation. Sound good? Here we go. When I said there's going to be a little algebra, what I meant was linear algebra. It turns out that there is a way to model classical computers. And when I say classical, by the way, I don't mean old-fashioned or Newtonian. I just mean everything that's not quantum. This is just the agreed upon term that non-quantum computers are called classical computers. And classical computation can be represented using vectors. A vector, just really briefly, is a collection of values, a well-ordered collection. For bits, we need to have 2 dimensions to our vector. And what I want to get at is that I'm going to go back and forth between representing these bits as labels on the top, but the underlying, quote, implementation of these labels is a vector. So when you see a 0, we should think this 2-item vector right here, a 1 in the 0th index and a 0 in the 1th index, and a 0 and a 1 here. So just to build up some muscle memory, here's a 0, and here's what that vector is. Here's a 1, here's what the vector is. I want to stress that these labels that you see in blue are completely arbitrary. They're just meant to be labels that stand for the vectors. Sometimes when we talk about vectors, I'll be showing the vectors. Sometimes when it's fine as a shortcut for visual aid, I'll show these labels.
Hey, Thomas. Sorry.
Yes.
Sorry. Can you kill your video? Because it's the audio is getting real bad.
Oh, good. How's this?
All right. Thank you.
The audio getting tolerable?
Oh, so very much better. Thank you so much.
Yeah.
Oh, thank you. Yeah. It must be Netflix time in my neighborhood right now. Okay. So the last thing that I was trying to hammer on is the equality between these two. And as we talk through this, I'm going to be switching back and forth between talking about a bit this way. Here's the 0 bit. And we're supposed to think this vector, or sometimes you'll see this vector and we need to think that's the 1 bit. I know what that is. Okay. So Now we're getting familiar with talking about bits as vectors. We can say that the operations on bits, vector, it's that bit. This is one way to show the NOT gate. It's this diagonalizable, it's in a way a flip-flop of the identity matrix. And what it does when you multiply this matrix by this 0 bit, say 0 times 1 is 0, 1 times 0 is 0, 0 up here, 1 times 1 is 1, 0 times 0 is 0, 1 down here, that's the flip from 0 to 1. Similarly, just to prove my point and drive it home, if you do not 0, we all know what that is. That's 0. You can compose these gates, and I won't belabor you with the mathematics, but when you multiply this all out, you actually get the identity gate, and the identity times the 0 bit is just the 0 bit. So not happens to be the identity. Not sure if it seems more elegant to be looking at it with matrices, but the point is you can express all of these gates using matrix multiplication. Okay, it turns out that this whole time that we've been talking about individual bits, we've actually just been talking about qubits. Qubits are a generalization of those two different bit vectors that we saw. All a qubit really is, for our purposes, is a mixture of the two bits, of 1 and 0. We might hear this notion that it's 1 and 0 at the same time, and there's a little truth to that. It might not be the way that I would put it, but English kind of runs into shoals when we're trying to get this concept across. Mathematicians will use the word superposition, and what we want to think about is there's a little bit of 0 and a little bit of 1. The reason I don't like saying it's 1 and 0 at the same time is that it's not absolutely 1 and 0. It's a mixture of them. It's a balance of them. I'll show you what I mean by showing these vectors in a graphical way on this good old-fashioned Cartesian graph. Let's think of the 1 bit and the 0 bit as two different axes. Or if you're into linear algebra, we could call them two different bases. There's 0-ness and 1-ness. And when you have a 0 vector, the 0 bit, the 0 vector, it's 100% 0-ness and 0% 1-ness. Similarly, this 1 up here is 100% 1-ness and no 0-ness. You can think of these like two different coordinates. This is 0 on the x-axis and 1 on the y-axis. 1 on the x-axis and 0 on the y-axis. But let's throw out x and y. We're talking about 1-ness and 0-ness. Okay? What these components of the two bits represent, what the components of the qubit in these two bases represent, is the chance that we have of observing a qubit as a 1 or 0. It's this probability is proportional to how much 1-ness there is or how much 0-ness. To be really precise, it's the amplitude in the 1-ness direction squared of those components. So what I mean is that when you look at the 0-ness and the 1-ness of these bits, you can square the separate components, and that'll be the probability of seeing a qubit in one of these two states. 1 squared is 1, 0 squared is 0. There's a 100% chance of seeing this qubit as a 0. 0 squared is 0, 1 squared is 1. There's a 100% chance of seeing this qubit as a 1. These amplitudes of 1 and 0-ness, when you square them, they have to sum to 1. And what this reminds us of is a probability distribution. That's just how probabilities work. When you sum them up, all of your possibilities, you should come to 1. And hey, I think we know what x squared and plus y squared equals 1 looks like. it resembles this unit arc right here. So here we have what a qubit can be. It can be any value in between zeroness and oneness. It's a mixture of the two. And the components of zeroness and oneness squared, they always will sum to 1. That's just what this graph is right here. In this case, they both sum to 1, and I picked a point halfway in between. 1 over this root 2, 1 over root 2. If you square that, that's 1 over 2. If you square this, that's 1 over 2. That sums to 1. So this is a valid state for a qubit. So if the qubit is in this state and we choose to measure it, that is to look at it, we're going to see it as either a 0 or a 1 with equal probability. There's a 50% chance, we square it to get the probability, a 50% chance of seeing a 0 and a 50% chance of seeing a 1. I'm just going to pop this vector out to kind of give a visual aid of what we're talking about. There's a 1 over root 2 zeroness and a 1 over root 2 oneness that makes up this qubit state right here. But it doesn't stop there. A qubit can actually be anywhere along this unit circle. It's completely valid for a qubit to be in any of these states so long as it obeys this equation that the zeroness squared and the oneness squared equal 1. And in fact, although we're not going to get into this because it's difficult to draw, qubits can even have these probability amplitudes in the complex plane. So not only can they be any real number between 1 and -1, but they can be any complex number. The amount of zeroness is any complex number so long as that squared plus the oneness squared equals 1. So if we wanted to represent this with complexity also, with the imaginary numbers, we would see something like a sphere is usually the way that you do this. It'd be another axis coming out of here. But for our purposes, we can just stick with the real numbers. So this is what we mean with the variety and the richness of qubits. The state of a qubit is a generalization of a single bit spread out over this whole circle, which when you factor in imaginary numbers becomes a sphere. And a qubit can occupy any of the states so long as it follows this one rule. So this is the material that we get to leverage and work with when we're doing quantum computation. Pretty neat. I want to pause for a breath here. I just threw a lot of linear algebra out. I don't see any questions in the chat right now. If not, we can just keep proceeding and start talking about, oh, here we go. So a quantum state exists irrespective of its representation. You project it to a vector space representation. You should still be able to get the original vector back, for example, an identity property, hence an idempotent operation. That is true. And we're going to get into this as we're working with how you operate on a qubit. Just looking forward as a bit of a spoiler, a qubit can be any of these states on this unit circle. And so all of the operations that we deal with are basically rotations around this circle. This is what it means to compute with quantum computers. With bits, it's kind of an abacus operation. The bead is down or the bead is up on an abacus. With a qubit, it's like the bead can be anywhere between up and down, and it can also be negative down and negative up, and complexly up and down. The bead can be in any of these states. All right, yes, Matthew, it is a unitary rotation. Okay, we're gonna talk about something that is an interesting fact about quantum mechanics, something that to this day, after about 100 years of developing this.
Uh-oh. We lost him.
Hey, am I back?
Oh yeah. Hi, Thomas. You're back. Yes.
Hi.
That we lost him, or he was in a different quantum state.
Yeah, I went into the multiverse for a second, but then one of you looked at me, and I came back. My screen sharing is disabled. Would you please give me
Yes.
the
There's actually two of you, which is weird.
manpower? There's two of me. All right, what I saw was Chrome saying "ah snap" and then it crashed. I don't know.
There's
what-
What we see is you superimposed in the meetup.
Host disabled attendee screen sharing. Gosh, I don't know I don't know how to reoccupy my former life to get screen sharing privileges.
Okay.
Try now.
Oh, got it. Okay. Here we go. All right, back to classical reality. The joke was I slipped into some quantum state, and then when I got back in Zoom, after being in this superposition of two different versions of me, once you observe a qubit, it becomes what it is observed as. And I want to think of this quite literally. Measurement of observation is a destructive operation on qubits. Yeah, Schrodinger's Thomas. He's gone. When you look at a qubit, it will move from this rich state to one of these two known states. Let's think about this for a second. So we're back at that 1/√2 qubit, which I wrote out. It was a floating point number right here. In a certain sense, in a certain very real sense, it would take an infinite amount of information to describe this qubit. It's kind of like all that information is wrapped up inside of this tiny state. Nature somehow contains this within a particle. But if we think of a qubit like some resource that we can use, when we observe it, when we extract information out of it, it's like a qubit can only be tendered as good for 1 bit. It only yields 1 bit. Once you look at it, the zeroness or the oneness, which is its state, represent the probability of seeing it in a 0 or a 1. What you will see is a 0 or a 1. I should say that I am not a physicist. I'm a programmer. I'm a coder. I'm sure there are people in this meeting that know more physics than I do by orders and orders of magnitude. So with that caveat, I'll say that an example of a qubit could be the spin of an electron. That spin is a two-state system. And let's imagine a spin as a two-state system. It can be up or down. This is the quantumness of quantum mechanics, that although nature seems to be continuous, it only presents itself in these quanta, in these discrete packets of information. When you observe an electron, it's only allowed to be in one of these two states, up or down. Everything having to do with this unit circle is kind of the secret life of the electron, the secret life of the qubit. It exists in this probability space, but once you observe it, it famously collapses to one state or the other, and all that rich information is lost. An example with showing this in action is using polarizing filters. And I highly, highly encourage you to round up some polarizing sunglasses in your house, or go find some great YouTube videos showing this experiment that drives home the fact that when you observe a qubit, it becomes what it's observed as, and all the previous information gets wiped away. What we're seeing right here is an actual quantum experiment that you can do at home. Light has these two states to it, and it's called polarity. And polarizing filters are a way of making a measurement on light to see what kind of polarity it has. What we're seeing right here is a big old mess of photons coming into this filter. And this filter has one type of polarity that it lets through, up polarity. And light is either polarity horizontal or polarized vertically. So when we have this polarizing filter oriented like this, that's performing a measurement, and it allows roughly half the light through. Now, all the light that comes through is polarized upwards, or I should say polarized vertically, and no vertical light, think of it like it's 100% vertical, no vertical light has any of the horizontal polarity. And so none of it gets through. When you perform an experiment, you'll have a 0% chance of a photon getting through here. You've taken another measurement, and there's no chance. The chanciness, you see, is when you measure it, say, at an angle. That's like saying, I start with a cubit in this position, and then I take a measurement right here, and it has a 50-50% chance of falling back into one of these two states. When you put this angled filter right here, half of this half gets let through, and then the horizontal filter lets half of that through. So the weird thing here is that adding another filter allows more light to come through. Although these two filters are exactly the same as they were right here, adding an additional filter intuitively should block all of the light, because should at least block more than what we were seeing. But adding another filter paradoxically makes it so that more light finally cuts through the last filter. And that's because, in a very real way, performing this new measurement erases all of the information about this photon. If we ask the photon here, are you polarized vertically? The photon would say, yes, I am. If you'd ask the photon here, are you polarized vertically? The photon would say, maybe I am, maybe I'm not. It's a 50-50 chance. Okay, so back to our linear algebra. We looked at that NOT gate earlier. Well, it turns out that NOT gate is perfectly valid to use as a qubit gate as well. We just generalized bit vectors to be qubits. We're going to generalize these classical gates to be quantum gates. And a gate is simply any matrix that respects this law that we have about a qubit's balance. The law being that 0ness squared plus 1ness squared equals 1. Someone in the chat mentioned that these gates have to be unitary, and that's exactly the right technical term for it. That's
Hey,
just
Thomas?
to say that these gates, yes.
We have a question. Would you like me to read it out?
Okay. Oh, I can read it.
Perfect.
Okay, so we assume that we're working with something with two quanta, spin for certain particles. Could you, in theory, make a bit with something like momentum, neglecting the difficulty of physical measurement, that has infinitely many quanta? If I understand the question right, could you make a qubit which has infinitely many quanta? A quantum integer. This is a great point. Could you have, I see how qint, as in you've got your longs, your doubles, your shorts, and then your quantum integers. In a way, nature does take an infinite amount of information to describe the state of any qubit. And what we mean by amount in this case is the quantity of bits it would take to describe this number. This number goes on and on and on and on and on. To perfectly specify it in bits would take an infinite amount of them. It's a floating point number that goes forever in principle. But nature is arranged in such a way that quantum mechanical systems can only be observed in a discrete amount of states, in a discrete set of states. That's the big surprise with quantum mechanics, that when we looked close enough at light, we saw that it wasn't a continuous wave, but rather came in these discrete packets, and we couldn't observe anything in between them. So the question of whether or not we could make use of these as resources and somehow encode an infinite amount of information and pass it on is a great question. And it turns out, sadly, that's not allowed by the laws of quantum mechanics. Think of it this way. I could take the work of Shakespeare and encode it in binary and then rotate my qubit in such a way that the binary expansion of this number is Hamlet. And then I hand you that qubit and I say, take a reading of it, and you'll get all of Hamlet in this one electron, in this one qubit. Well, as soon as you look at it, it's going to collapse to one of these two states, and all you will get is the first bit of what it was that I was trying to say. And that's all a qubit can be good for. Hope that answers the question. Okay, so now we're going to generalize gates, and we're going to work our way through these to start building up some algorithms and eventually work our way towards teleportation. So a gate is something that just keeps respect of the balance between zeroness and oneness with a qubit. What I mean by respecting the balance is that the gate is unitary, and what I mean by unitary is that it's just a rotation around this circle. Here's what the X gate is. It's just hopping from one state of the unit circle to another state. And this is all that we're going to be doing when we're making our algorithms. It's kind of like an old-fashioned state machine in the sense that you're in one state, you apply a gate, and it'll take you to another state, still on this circle. And as we saw earlier, not 0 is 1, and not 1 is 0. But now we're in the quantum world. And so these knots start to lose their sense once we're dealing with these superpositions, once we're dealing with these genuine quantum states. Not -1 is not -0, and not whatever this is, just is itself. Because what's the NOT gate really doing? It's inverting this vector right here. It's taking the zeroness and moving it to the oneness spot, and vice versa. Here's an example with the linear algebra that we looked at earlier. Multiplying this matrix on the 0 bit gives us the 1 bit. Multiplying this matrix on whatever this state is called gives us that state up there. And then here's another gate. We call it the H gate, and that's short for Hadamard, which was the fellow that this gate was named after. And what this operation does is slides our qubit out of some classical state and into this superposition state right here. Or it slides a superposition back into a classical state. Now, when I say superposition, I just want to repeat myself so we have no ambiguity as to the term. It just means that combination of zeroness and oneness. It's a very ponderous, profound sounding word, but that's it. Superposition is that you have some zeroness and some oneness. It's a mixture of the two. We'll move from this lopsided superposition of oneness into this even superposition of -1/√2 zeroness. I'm sorry, +1/√2 zeroness and -1/√2 oneness. And why is this still a valid state? Because zeroness squared plus oneness squared needs to equal 1, and this one does. Another way to represent the H gate, maybe it's a little easier to see what's going on, is by factoring out that 1/√2. This is the operation that we're seeing. So when we take H of the 0 qubit, we know where that takes us, right here. And to just prove the point with matrix multiplication, you can see it as these two basis vectors that can factor out from the vector added up right here. That this is an even superposition of zeroness, an even superposition of oneness. H of 1, similarly, but differently, there's a negative sign in here. So it takes us still takes us to an equal superposition of the 0 bit and the 1 bit, but there's this negative sign in the mix. This negative sign, for our purposes right now, is pretty important, that these two states are mathematically distinct from each other. One of them has a negative here. And this matters because we need to be able to get backwards and forwards from one state to the next. So it's not enough to say that one, when you apply the H gate to it, takes it to an equal superposition. We have to know which one exactly, because that's the one that then when you apply H returns you back to 1. Okay, I want to clear the queue of questions really quickly. So one of them is what's this negative thing? What do I mean when we say there's negative zeroness? Now, the way a mathematician might speak of these is that what we're talking about with zeroness and oneness is an amplitude. That's a technical term, and amplitude is meant to be, if you saw this as a Cartesian graph, how far along the axis are you? So in this case, we're in a -1 amplitude along the 0 axis. And in this case, we're at a +1 amplitude along the 1 axis. So this has a 1 amplitude and oneness. This has a -1 amplitude and oneness. As far as these negative signs go when it comes to observing it, they don't make any effect with a single qubit, because when we square these amplitudes, the negative signs go away. That is to say that this qubit and this qubit each have a 100% chance of coming out as the 1 bit. If your qubit's in this state, or if your qubit's in that state, there's still a 0% chance of observing it as a 0. There's a 100% chance of observing it as a 1. And in this state right here, what's the chance of seeing it as a 0? Well, 50%. This one right here, what's the chance of seeing it as a 0? Also 50%. Same here and same here, because we square the amplitudes to get the probability. This is an axiom of quantum mechanics. And there's a raging discussion to this day about why exactly that is. Okay, another question. Upon observation, because of the squaring, you don't actually observe negatives. This isn't a question, this is an answer. It only, so the answer goes, it matters that we have these negatives because we're dealing not with probabilities directly. We're not talking about negative probabilities, but amplitudes in certain directions. And this really harkens back to the day when we thought of all things as waves, thought of light as waves. The notion of an amplitude, that technical term, dates back to when physicists were talking about this stuff as waves. Superposition also dates back to that. Superimposing two waves on each other and looking at the amplitudes of waves is where all these words that we're stuck with today came from. Okay, so we've done 2 gates. The next gate, which does this, and the H gate, which does that. You can almost think of these gates like chess moves, that you have different pieces and they have different legal moves along the chessboard. This is a very strange chessboard. It's a circle, and you have to stay along the perimeter. But every gate is a rotation along this circle. Okay. Let's put these gates to work. We're going to send a qubit along a journey around the unit circle. Since these gates are just matrices, we can compose them together to create new gates, or we can chain them together in this composition to create some sort of primitive circuit for our qubit. And the composition of matrices is simply matrix multiplication. Let me show you what I mean. We want to take a qubit from a known state, the 0 bit, and we want to get it down to -1, this very strange -1 state that we've been talking about. Well, no single gate that we know of is going to get us there. So just using X and H, how are we going to do it? let's start with an X, and that move takes us up here. And now, if I were to apply X again, I'll just end up on my hero's journey right back to where I began at this 0 bit. So I'm going to throw in a different gate and see where that takes us. The H gate is this sliding action that takes us down to an equal superposition. Okay, this is good. I think I can see how I'm going to leverage this from here. I'm going to X, and that's going to take me up to this point, because X is the flip-flop. The zeroness gets sent to oneness, the oneness gets sent to zeroness. So X takes us up here. And then finally, that H slide takes us down to -1. So we did it. Congratulations. This is a quantum circuit. It's not a very interesting circuit, but it does compute a qubit from the 0 state to the -1 state. And I cross my heart, this is what quantum computation looks like. It's simply applying these matrices, these operators, to vector spaces. Someone somewhere once said that all of quantum mechanics is contained in linear algebra. And I think there's a high likelihood of that being true. There's a lot of trueness in the superposition of that utterance. We're going to do a bonus gate, just for fun, just in case we're not having enough fun. Here's a bonus one, phasing. So I've been saving this term, even though we've been talking about it in the chat. When we are talking about positivity and negativity of these amplitudes, the term that you'll hear in the literature is phase, that qubits and particles have a phase to them. That's something that, like we saw, doesn't affect the probability of observing it directly, but it is represented by this negativeness or this positiveness. This qubit is positively phased or negatively phased. And this has no correlate to the classical world. This is just a quantum property. And it's something that, as you're going to see in teleportation, we make use of to get some information out of qubits and make them do our bidding, is that it's not enough to simply say that the qubit is a 0, but you can say, what phase of 0 is it? So phase doesn't affect the probability of being measured in a state, but it is meaningful information that these qubits carry with them. Okay, so we should be pretty comfortable with this unit circle with a qubit. All of the gates that we've looked at are really rotations when you get down to it. Phase is like rotating it along this axis. It'll inverse the whole qubit, sending this state down to here. These states say exactly the same. The X gate is an inversion or a reflection, more precisely, around this axis. If you can imagine some sort of diagonal axis, that's all the X gate does, is it reflects the qubit along there. And the H gate is this slightly less than 45-degree axis that it inverts the qubit along there. Phase is just that. They're very, very simple things, but once we add them up, they become extremely powerful for certain problems. So let's do this one more time with our new gate. How are we going to get from 0 to -1? Well, the X gate on 0 takes us to +1. So what should we do now to get down to -1 in one gate? We'll apply the C gate to phase it, and that's it. 2, and we are home. So now we have a more sophisticated, a richer circuit, something more meaningful and easier to convey. We X, and then we Z, and that's it. Okay. Pause for breath. That was 1 qubit, and we are locked and loaded with almost all the knowledge that we need to work our way up to genuine quantum algorithms. All we need to do is generalize now into the world of 2 and more qubits. Any questions? I think a lot of us are muted, so we can't have cocktail chatter, although that's welcome if expressing things over chat is going to be difficult. By the way, we'll want to leave time at the end to Q&A and talk through this stuff. Okay, So we hear about exponential speedups with quantum computers, that they're exponentially faster than classical computers. Why is that? Well, one of the main motivators behind that fact is that the state space, the combinations that qubits can occupy, that unit circle that we saw, it grows exponentially as you add more qubits to them. So looking at a single qubit, we have two different, let's call them two different components to this. It's two-dimensional. It has zeroness, it has oneness. When we have two qubits, we have to think of it as zero zeroness, zero oneness, one zeroness, and one oneness. Each possible blending of these zeronesses and onenesses are represented in the relations between the two qubits. Now, 4 is 2 to the second power. As we're going to see later, when you add a third qubit, now we're going to have 8 states to carry all of this information, and on and on and on. And by the time you get to about 50 or so, 2 to the 50th power is just about the limit to what any supercomputer in the world can keep in memory. Okay, back to this notion of vectors and labels. So we're generalizing, we're expanding our horizons. When I say 0, 0, 0, zeroness, this is the vector that goes with it. It's just this right here. A 0, 0 qubit is 100% 0, zeroness. 0, 1 is 100% 0, oneness, and on and on and on. And now a superposition of these 4 different states is a combination of any of these states, such that when you square them, it all sums to 1. Just the same thing. Think of these like the amplitudes, which squared are the probability of seeing a qubit in any of these states. So here's a perfectly valid 2-qubit state right here. It's a 25% chance. Why am I saying 25%? Because 1/2 squared is a quarter. It's a 25% chance of seeing it as 0, 0, 0, 1, 1, 0, 1, 1. I'm breaking this out into, in linear algebra, we would call the basis states. I'm breaking it out into its bases and showing that this is a 25% chance of 0, 0, a 25% chance of 1, 1. Okay? But superpositions don't have to be equal. They can be any blending that we want. This simple 2-qubit state is just 1, 0. That's it. No funny business. If I handed you a qubit in this state, if I handed you 2 qubits in this state, and you measured them both, this is what you see, because you have a 100% chance of seeing it in 1, 0. All right. This is the last bit of math that we're going to introduce. The relationship between these vectors and this larger vector, between these basic single qubit vectors and the 2-qubit vector, it's called a tensor product. And although we haven't, maybe we haven't all used this term before, I think it makes intuitive sense. As we start playing with it, we'll see why. It's this strange sort of interleaving of vector multiplication, where you take this spot and you multiply it by this one and this one, and then you take this component and multiply it by this one and this one. You lace them together like this. That's called tensoring 2 vectors together. And as you can see, it exponentially increases the size of the vector. So when I tensor 2 bits together, I get this 4-element vector. Okay? We've seen these tensors before in probability, and this is my contention that this might make intuitive sense, is that let's think of having 2 coins. You have a coin and another coin, and each coin can be expressed as these probability vectors of seeing it in heads or tails. This is the old qubit as coin analogy. And so I flip a coin, there's a chance of seeing it as heads, there's a chance of seeing it as tails. You have a little bit of headsness, a little bit of tailsness. Now, when I take 2 coins and I want to ask what are the chances of seeing it as heads, 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 tails, tails, heads, or tails, tails, well, that's the tensoring relation. I'm going to take the chance of seeing it as heads and multiply it by the chance of seeing it as heads here and tails there. Same thing going on right here. I multiply this in, I weave these two vectors together, and you get this distribution. 50, 50, 50, 50, tensored together is 25% all the way down the line. This is the probability table that we would see. That's tensoring. Okay, so if we take away one thing from this talk, it's that new word, that tensor relation shows up in probability. Okay, out of that sidetrack, back into quantum soup. We're now dealing with 2 qubits at once. We've got 4 components to these things. What we need to operate on them are matrices that are not 2 by 2, but 4 by 4. Because again, operating on qubits is just matrix multiplication for all that we're concerned about. Let's talk about a 2-qubit gate. This is my favorite one. It's called controlled X. And after this talk, if you go look up quantum computing out in the internet or in books, you're going to see it represented as this dot with a line pointing to an X. We think of this dot like it's the control, and we think of this X like it's the gate that operates on another qubit. It's a gate that takes 2 qubits in and outputs 2 qubits. It's almost like an if-then. It's like our rudimentary if in quantum computing. What this is saying is if the top qubit is a 1, then apply the X, else do nothing. And over on the right, I'm showing this in matrix format, just so I guess like Neo seeing the matrix, we understand what's underlying all of this. There's no magic going on, it's just basic linear algebra. And if you want to take these slides and work through this and do the multiplication, you'll see that it all works out, clean as a cat. Okay, so 0, 0 gets sent through this gate to 0, 0, because we're saying if it's 1, apply the X, otherwise do nothing. So we do nothing. 0, 1 is also doing nothing, because the 0, what we call the control bit, is doing its controlling by very passively doing nothing. The if didn't check out. 1, 0, here's where it gets interesting. 1 as the control passes, and so the X gets applied. And now we have 1, 1. That's the output of this state. 1, 1 coming in gives us 1, 0. So it's this matrix right here multiplied by these 4 different vectors give us the 4 different outputs. Here's a little cheat sheet right here. This matrix takes this state and maps it to that one. This state maps it to that one. 1, 0 goes to 1, 1. Why is that? This is the control bit. This is the bit that gets knotted. Control not. Control X. Easy peasy. If you want, I'm not sure how you see matrices, but sometimes I look at these like each row represents one of the basis vectors. And this is saying that it sends 0, 0-ness to 0, 0-ness. It sends 0, 1-ness to 0, 1-ness. And it sends 1, 0-ness to 1, 1-ness. What I'm appealing back to is okay, it happened again. This is one of the problems with quantum computers, is that they're very, very noisy. And you might be going along with your algorithm for a while, and then noise and entropy inevitably take over. And your experiment, running smoothly, starts to veer off in directions that you did not foresee or plan for. Are we back? Is the appropriate screen sharing?
You're good.
This Chrome keeps crashing. Cool. All right. So we're cooking with gas. We've got 2 qubit gates going. And this is really all we're going to need to do all of our work at this point. But just to make sure we're following along, we're going to do a quantum quiz. We're going to see what this gate does. So I'm giving you a matrix, and I'm showing you what this looks like graphically. Looks a lot like the controlled X, but now it's the controlled Z. Z was our friend, the phase gate. So either looking at this matrix or looking at this graph, what's this going to do? If we pass in 1, 1 into this gate, what do we get out? Well, the control bit always stays the same, so that's going to be a 1 on top. This thing sends 1, 1-ness to negative 1, 1-ness. Does this right here. That will take a state of 1, 1 and map it to this state. And then this one right here will take 1, 1-ness and map it to just 1, 0. Sorry, let me open the chat. Okay. My apologies. When my browser crashed, I lost the old chat. So if there were questions that I'm not answering, I'm sorry, they've been erased with my new quantum measurement. All that information is gone as if it never happened. The question is that dot down arrow always the controlled operator? Yes, this is a common picture. So when you take this information and go on your own quantum journey, learning this, you're going to run into pictures showing the circuit. And this is the agreed upon way of showing the circuit for quantum. This dot represents a control where if I'm 1, I do the thing. If I'm 0, I pass on the thing. Why is it not negative 0? That's a good question. Let's go back to what the Z gate does. The Z gate sends 0 to itself. Phase gate, incidentally, interestingly, importantly, does not change a 0 state, nor does it change a negative 0 state. Why that is, I'll leave it to you to puzzle in our copious amounts of shelter-in-place time. So this thing just sends 0 to 0. It doesn't move it at all. Okay, big idea. Qubit combinations of possibilities grow exponentially with more qubits, just like coin tosses. 2 coins, you have 4 different outcomes. 3 coins, you have 8 different outcomes, and on and on and on. When we have 3 qubits, we need to keep track, we only need to keep track of this if we're using a supercomputer to run a simulation, but nature keeps track of it just in the quantum particles themselves. It'll keep track of all 8 states. Once you have, let's say, maybe 50 or so particles together, it can fit on the head of a pen, but we can't keep track of a vector that large in a supercomputer the size of a Walmart, which is, I think, a fascinating fact. Okay. As we end this phase, quick recap, just vocabulary. Superposition. When we hear the word superposition, going forward, whether we're mathematicians, physicists, or just reading pop-sci articles, all that means is that mixture of 0-ness and 1-ness. Operators, gates, all they are these matrices, these unitary matrices. Unitary meaning that it respects the length of the vector. The amplitude remains on the unit circle. It's just a rotation around that unit circle. And then we also need to know, what is it about this exponential speedup? Well, it's that qubits can encode an exponentially large amount of information as you add more qubits. Add another one, and you've doubled the amount of information you're dealing with. All right, gang, this is going to be fun. Now we're going to talk about what entanglement is using our mathematical framework. And my hope is that at the end of this talk, we all walk away knowing clearly, once and for all, what the heck people mean when they talk about entanglement. There have been so many analogies and so many metaphors, and they do have value, but we're just going to look at the math and call it good there, and let the metaphors kind of follow from that foundation. So here you go. If the state of two qubits can be expressed as this tensor product of single qubits, then they are unentangled. Here's what I mean. You have I got my 1 qubit right here. I got my 0 qubit right there. I tensor them together to this state. Here's a state of 2 qubits. I may express that as the tensor product. Therefore, they are unentangled. Simple as that. It can be a little richer. It can be a little hairier. This is a perfectly fine 2 qubit state, but I can express it as the tensor product of 2 qubits. Therefore, they are unentangled. That's fine too. The real point with unentanglement is that if you know what the first qubit is, it won't tell you anything about the second. It doesn't imply anything about the second. If I observe this one and I see that it's a 0, what is the second one going to be? Well, if I know this is a 0, the second one could be a 1, or it could be a 0, because seeing this first qubit as a 0 is equally consistent with the second qubit being a 1. It's a way of saying that the states are independent of each other. This tensoring relation is a pretty elegant and straightforward way to represent this independence. Okay, entanglement is just the converse. If the state of 2 qubits cannot be expressed as a product of 2 single qubits, then they're entangled. But blam, that is all it is. Here's an example of one. It may not look like much, this state, but oh, did it cause a lot of heartache throughout the majority of the 20th century in physics. This is a state. This component squared plus this component squared plus this component squared plus this component squared, sum to 1. It's a perfectly valid 2-qubit state, but I will assert that it cannot be expressed as the tensor relation of 2 qubits. I can express it as an addition, as a linear combination of these 2 states. It's an equal superposition of 0-0-ness and 1-1-ness, but it's not a tensor relation between 2 qubits. Let's prove it really quickly. Let's say it is a tensor relation. This is going to be a classical proof by contradiction. So I have some qubit and some qubit, and when I tensor them together, I should get this state. So these are numbers. This one's A, this one's B, this one's U, this one's V. When I tensor them together, you get this lacing effect. And now let's look at how this should equal that. So A times U should equal 1 over root 2. A times B should equal 0. B times U should equal 0. B times B should equal 1 over root 2. But wait a second. In order for this to be 0, either A or U must be 0. But I'm sorry, this is a B. But in order for this to be 0, either B or U must be 0. But B can't be 0. Otherwise, this would be 0. U can't be 0. Otherwise, this would be 0. This is ridiculous. It's absurd. It's impossible. It's entangled. This is not, it can't be a tensor relation. This is a perfectly valid state for qubits to wander into, but you cannot express it as the product of 2 qubits. They are entangled. All right. What do we mean about this independence? Let's one more time look at the coins. So I'm tensoring 2 coins together, and they have 4 possible outcomes. We all know that coins are independent. When I flip the first one, it doesn't tell you anything about what the second one will be. That's the tensoring, that's the independence. The probability is evenly split up over all of them. Let's say it is heads. What's the second one? Well, that's a 50-50 chance of being tails or heads. Because when I measure this one as heads, it's going to be either this state or this state with an equal probability. But if we had quantum coins, we could carefully arrange them in our laboratory so that they embody this probability state. The coins are now correlated in a way. What this means is that, let's say I give you some quantum coins and they're in this state. You know that this is their probability table. What happens when you flip the first one? Well, are you going to see heads? Are you going to see tails? I don't know. There's a 50-50 chance of seeing heads or tails with the first one. Let's say you see heads. Now, what's the second one going to be? Well, we know that we're in either of these two states, and this state has a 0% chance of happening. This means that when you see heads with your first coin, you're guaranteed to see heads with the second coin. They're correlated. They're entangled. Knowing what the first coin is implies what the second coin is. To know the state of one entangled qubit implies some knowledge about the state of the other one. That's entanglement. These qubits aren't independent anymore. And experiments have verified time and time again that you can take these entangled particles, move them to separate areas, distance them in space and in time. And then when you measure one of them, you may not know what you're going to get, but based on the measurement, you know what the other one will be. I could give JJ one entangled qubit from an entangled pair. I've got the other one, and I go drive to California with it. And then I perform some experiment and I measure it, and I see that it's a 0. Now, JJ's kept his in the freezer this whole time. Doesn't matter when he chooses to measure it, but when he does, I guarantee that he'll see a 0 as well. That's what entanglement does, and this is how we represent it mathematically. And it's really nothing more than this. You can't show this as a tensor product. All right, let's make a more sophisticated circuit. We want to entangle some qubits. This is all nice on paper. Let's see how you actually do this with a circuit. Before so, I want to make sure I'm answering all the questions. One question is, as everything we've talked about so far, can that be done by classical computers? Oh, prior to talking about entanglement. Classical computers can simulate the bejesus out of this, because at the end of the day, it's just linear algebra. These become very large vectors, but simulation is tractable so long as RAM and hard drive space doesn't run out. You can simulate this tensor relation until you can't anymore. And this is what we've been doing for so long when trying to, say, simulate reactions between two chemicals. In material simulation, you set up a hydrogen atom and a helium atom in a simulator and see what happens. The problem is when you add a few more atoms, it becomes very quickly impossible for our computers to keep up with the state space of this. Enter quantum computers. Let's let nature do what nature does best, which is be quantum. Okay. We like entanglement. We use it for all of the important algorithms that are out there. How do we get it? It's actually super easy to do. We want to take two qubits, let's just say they're in 0, 0, and massage them so that we get into the state where we have an equal chance of 0, 0 and 1, 1. Let's write the quantum algorithm. The problem that we've set ourselves is starting with this state. How do you get to that state? Starting with 0, 0, all 0, 0-ness, how do you get to this even-Steven split between 0, 0 and 1, 1? Well, we've seen these 1 over root 2s before. That certainly makes me think of our Hadamard gate, the H gate. Remember, the H gate on the unit circle slides that 0 up to that equal superposition. It slides it up to this state. And when we apply it just to the first qubit, the second one stays the same. And now we have this relation. Now I'm showing off to the side that we're tensoring these two qubits to get this. So I'm making the point that the tensor relation holds. They're uncorrelated, they're independent, they're unentangled, but we're getting close. Here's another way of looking at the same state right here, is we have an equal superposition of 0-ness and 1-ness tensored with a 0. It's half 0, 0, it's half 1, 0. This is 0, 0-ness, this is 1, 0-ness. I'm just playing with the terms. factoring things out to work my way down to this label notation. Because in this case, I think throwing out the vectors and using our labels makes it a little easier to grok what's going on. So we're looking at an equal split between 0,0-ness and 1,0-ness. If I measure the first one and it's 0, does that tell me what the second one is going to be? Oh, then it doesn't tell me anything new. I already knew the second one was 0. If I see the first one as a 0 or a 1, it doesn't imply anything about the second qubit because they can be broken up. Now, what we need is a gate that plays with both qubits at the same time. We need something bigger than a single qubit gate. We're going to bring back our old friend, my favorite gate, the controlled X, controlled not. Remember, this one does something pretty sneaky. It does nothing half the time. And then for these other two states, it flips the other one. So it'll map 1, 0 to 1, 1. What we're trying to do is get this one to be 1, 1. So we have an equal split of 0, 0, and 1, 1. I think we can use this control not. When we run the controlled X gate on this state that we got from using the H gate, there we go. It flips 1, 0-ness and 1, 1-ness and moves us into superposition. So that's it. This is the trusty, famous entanglement circuit. 2 gates. The algebra is off to the side for you to pursue in your leisure time, but that's all you have to do to take 2 qubits and move them in to this entanglement. This is what we get at the end of it, an equal split between 0, 0, and 1, 1. This means when I flip the coin, I take the measurement, I have a 50-50 chance of seeing 0, 0, because 1 over root 2 squared is 1/2, and a 50-50 chance of seeing 1, 1. If I measure the second qubit and it's a 1, and then JJ takes the other one and runs off to Acapulco, I know that it's going to be a 1, no matter what. This is the spooky action at a distance that Einstein made so much noise about. And it turned out to be verified experimentally in ways that unfortunately weren't available to Einstein in his time. He looked at this vector and saw that it's perfectly allowed by the rules of quantum mechanics. But what it means is that states can be correlated across space and time, because nothing about this vector implies that the particles have to be near each other or even in the same span of time. It's that no matter what, once we entangle some qubits, we can move them away from each other, and measuring one will imply some correlated knowledge with measuring of the other. Patrick was pointing out that this is often called the EPR paradox, which stands for, oh goodness, Einstein, Podolsky, and Rosen, I think. Gosh, I shouldn't have even attempted that. Einstein is the E in the EPR. It's a paradox only if you don't accept the weirdness of quantum mechanics. It's paradoxical because it seems that information travels instantaneously from one qubit to the next, but that's actually probably not the best interpretation of what's going on. It's not that the qubit moves information across space and time, but it's that, Rosen, yes, thank you. But it's that the qubits are correlated with each other. Correlated in the way that my left shoe is correlated with my right shoe. It's something that is a very mundane fact, but it's strange when we're dealing with probabilities, that probabilities can be correlated to each other. Okay, I want to pause here and go over what we covered, because we have half an hour left in this meetup, and we can try to squeeze in teleportation, or we can open the floor for discussion. So leaping forward to the summary, I want to stress that we worked with bona fide quantum circuits and quantum algorithms. And I mean that with no exaggeration. That when we take this talk and go on our own journeys with learning this, there will be little more to this than what we've already seen. There'll be several other gates that we didn't talk about, but that's really it. All that we're doing when we're doing quantum computing is applying these rotations and reflections to these qubits. And all we mean by qubits are these superposed mixtures of zeroness and oneness. A professor at UT in the quantum computing department, Scott Aronson, who is a brilliant writer, said maybe the best way to put it is that quantum mechanics uncovered a new ontological category in reality called maybiness. It's not that it's 0 and 1 at the same time, but there's some reality to the maybiness of 0 and the maybiness of 1. We don't know what that means. We don't know the best way to put it in English, but that's what's happening in a way when the qubit is rotated in some sort of superposition, that it's a little bit of maybiness. And yeah, as we all know, working in DevOps, this sort of superposition and indeterminacy, this maybiness, appears all over the place when we're trying to debug things. So the chance of seeing a qubit in a 1 or a 0, knowing that we can only get 1 bit out of it, the probability will collapse. Chance of seeing it as a 1 or a 0 is proportional to the amplitude in that direction. So if you're just a little bit off of perfect 0, you might have a 99% chance of seeing 0 and a 1% chance of seeing 1. But that chanciness is there. The qubit can only be observed in one of 2 states. That's the quantum part of quantum mechanics. So even though there's this big, rich, beautiful, fluid continuum of maybiness that it can be in, once you observe it, once you take a measurement of it, once the coin stops spinning and it lands on the table, it's heads or tails, it's up or down, it's polarity this or polarity that, you can only get 1 bit out of it. That's all this resource is good for. Gates are just matrices. They preserve this balance, the rule that 0ness squared plus 1ness squared equals 1. And we can arrange gates in circuits. It's a model for writing algorithms. Entanglement, we can be as literary as we want in describing it, but it's that we can't talk about 2 qubits independently of each other. It's kind of like, I think Schrödinger said that knowledge of the whole does not imply knowledge of the parts. We know the whole state of 2 qubits, but that doesn't mean we get to know exactly the probability of either one independently, because they aren't independent anymore. And then we can talk about teleportation if we have time. Teleportation is just going to be a circuit that I'm going past. It's kind of a temptation, but it's just using the gates that we've learned. I want to make one more plug. Please scan this QR code or get the slides. The link to the slides is in the chat, and you can click this link to give feedback. And before diving into teleportation, my gut feeling is that doing a little bit of Q&A and open discussion would be more valuable for everyone's time. That's just my opinion. For what it's worth, I'd be happy to stay on extra if people want to go after hours to work through this circuit. So I don't know how we want to do this with Zoom. There are quite a few, couple dozen of us, but I want to talk through the chat really quick. So Perry was asking, do we ever know the actual value of the maybiness? Do we ever care? And the answer is emphatic yes, we do. We do know about the maybiness. The H gate is determined. And we get into this I think mode of thinking with quantum mechanics that is so probabilistic. Now, it's a little fuzzy, it's tiny whiny, there's a chance of saying it this way or that way, but at the end of the day, these are deterministic gates. Moving it from this state to that state is a known operation. And we know what this state is. It's 50-50, 0 and 1. It's right here. We have precise knowledge of that. We know what this gate is and what this is. And we know this not just abstractly, but when we make other qubits interact with each other through additional gates, the fact that the qubit is in this state continues to play an effect. It's very important to move the qubit in this state, and then we use that to compute. When we're talking about this whole unit circle being our palette, what I mean is that we know the maybiness, and we get this whole area as our playground. Earlier, I made a quick analogy to abacus beads, where a classical bit is this state or that state. The bead is up, the bead is down. Or on a classical computer, the filament is charged or it's not charged, or whatever medium you use to represent a bit. With quantum computing, we really do get to use this whole circle to encode information. The interesting thing is that when we observe the qubit, when we measure it, the probability collapses to 0, or it collapses to 1. The way that I heard this described is that quantum computing happens in this very dark and quiet, Zen-like space where no observation happens, and these rotations and quantum operations are free to move about in their quantum space. And then when the computation is done, you open up the lid and you see what you got. And what you're going to see is a big long string of zeros and ones, because that's all you get with your qubits. Just like with light polarity, it either passes through the sunglass filter or it doesn't. It's a binary measurement. This is the interesting thing. So long as we can stave off measuring, we can make use of all the colors of the wind in here. And that's the very fascinating challenge with quantum algorithms, which is how can you get them to work without making measurements? Since once you measure, you are back into the classical world. Okay. Patrick was making a comment about these correlations with entanglement, and that the correlation is instantaneous. And the meaning of that word, which is supposed to raise hackles on Einstein's neck, is that it's, quote, faster than the speed of light. Something is happening instantaneously across space-time. And the reason this does not, and I mean it, does not break with general relativity, is that it's not information that's moving. Flipping the quantum coin and seeing it become a 0 does not send information to the other. They are correlated to each other. They're not communicating with each other. So that correlation is instantaneous in just the same way that I can write a 0 or a 1 on 2 pieces of paper, and I know they're correlated. I know that, I know what they are. If one of them is 0, the other is going to be a 0. I write a 0 on 2 pieces of paper, and I send them to opposite ends of the world. You open up the envelope, you see the 0, you know the rules of the game. The other envelope must have 0. They're correlated. There wasn't instantaneous information between these 2 envelopes, but what there was is this correlation, so that your knowledge about the state is updated instantaneously. I'm going to risk using my video. If my audio drops out, I'll turn it back off. I'm waving my hands into the void right here. Okay. Is it good enough to know that the state is somewhere between 0 and 1? Well, for most quantum algorithms, in a way, no, although some of them care less. Sometimes you do want to know precisely the state between 0 and 1, but there are a class of algorithms where they have a way of amplifying, and I'm using that word in conjunction with our amplitudes, amplifying the good answers and dimming down the bad answers. And it's like you inch up the qubit along the state space on its way to an answer that you want. And while it's working its way, gradually amplifying, you're not totally concerned with the exact value of the superposition, but the algorithm has a way of moving it slowly from one space to another. This is called, the most famous example of this is Grover's algorithm, which, when you go look it up, it's the unstructured search algorithm. It's that if you have a filing cabinet with n number of cubbies, and I put a baseball in one of the cubbies, then at the worst case, you have to search all n of the cubbies. Big O of n, this operation. You could look in each one at a time, to find the baseball. But somehow, Grover was able to use quantum computing to do this in log n operations. You can find the tennis ball in the log of the number of cabinets, of the number of cubbies, which, like all things with quantum computing, is astonishing. You can search through an unstructured search through a database, not in linear time, but in logarithmic time. Okay, it's Grover's algorithm. Okay, how do we know the maybiness if observing it collapses into a 0 or a 1? That's a great question. If I handed you a qubit and you didn't know its background, you don't know where it came from, you don't know anything about it, you're just seeing it for the first time, I hand it to you in some sort of freezer. If you want to look at it, it could have been in any of these states, but as soon as you look at it, it just becomes a 0 or a 1. So you're never going to know what state it was in. That information is lost. It's like nature erases. Nature has no memory of previous states. All this rich maybiness with the light is lost when you observe it. When you observe a qubit, it becomes what it is observed as. It becomes a 1. So it could be anywhere here. It could be right here. And when you observe it, there's just this sliver of a chance that you'll see it as a 1. And even though I know that it was the tiniest chance, to you, you just see a 1. You have no idea where it was along this continuum. Okay, we can know that maybiness, though, if we understand the origin story for this qubit. So you can
Oh, he'll be back. It's okay. Thomas, you there?
Should we repost the questions that haven't been answered yet, since he loses the chat when that happens?
Yeah, I'll copy paste them.
All right, cool.
Yeah, thank you. Gosh, I even closed all my tabs. What do you want, Chrome? I know you're hungry for memory. How's the screen share going?
There you go. We can see we can see it.
Right.
And I reposted the questions also for you.
Yeah, thanks. So the answer is, if maybe I should try using Microsoft Edge. What could it hurt? So you start off with a 0, and then you run it through an H gate. Well, where does the H gate take it? The H gate takes it right to here. So do you know the exact state of the maybiness? Yes, you do. You can take a qubit and prepare it in this state, and then measure it, and it'll be a 0 or 1. And then you can repeat that operation 1,000 times, 1,000,000 times. And you'll see over the course of all of your measurements, roughly a 50% chance of a 0 and a 1. And that's kind of an inkling of how we experimentally verify that our gates are working. Just run it again and again and again and again, and you'll see the same probability. This is also how we verified this entanglement. I think recently China actually used a laser to teleport a qubit to a satellite that was entangled with a qubit that remained behind on Earth. And then they measured them and saw the entanglement in action spread out across the stratosphere. Okay. Still understand how this is more efficient than classical computers. Can you briefly touch on why you see the exponential speed up? Is it just because you can operate multiple bits on once due to entanglement? That is a great question. If we had more time, I would really enjoy going into an algorithm that shows the speed up concretely for us to get our hands on them. But suffice it to say that the exponential speed up comes from the exponential state space that you get to play with. That by adding 3 qubits and then 4 qubits and on, you get more than a merely linear or polynomial amount of work that's being done. If I add one other bit to my computer, I don't get the same exponential speed up. It's multiplying by 2. It's not raising to a power of 2. And I have 2 bits, and I have 3 bits, and 4 bits. It's like adding more beads to your abacus. Gives you a multiplicative factor, but not an exponential one. Generally speaking, all of the quantum algorithms make use of something called quantum parallelization. The more metaphysically minded would think of it like you're farming out the computation to different universes. This is the many worlds interpretation of quantum mechanics. A less far out interpretation is that the amplitudes contain all of this information in parallel, and the interactions between these amplitudes has this exponential richness to it. And out the other end, you can produce a result while running all of these amplitudes in, quote, parallel. There's a parallelization that happens with the exponentiation. And it really depends on who you ask how you want to interpret this. There are very intelligent people that will say it is as if we are harnessing parallel universes when we're making use of all of this maybiness to run our computations. There are also smart people that remain very agnostic about this. But the fact that this is the pattern, that you put qubits in some superposition so that there's a little bit of all of this, a little bit maybiness all over, well, now you have an exponentially large palette to work with. Okay, to what sorts of workloads does quantum computing lend itself, and why? When quantum computing was initially dreamt up in the armchair of Richard Feynman and other colleagues, the thought was simulating quantum systems. Everyone knew that there's this exponential problem with representing the states of quantum systems. They get too big, too fast. Classical computer can't keep up. And so the natural thought was, well, shoot, let's just let the quantum things simulate themselves. What we're trying to do is simulate quantum interactions. No better candidate for it than quantum particles with their quantum ways of being quantum among each other. Fight fire with fire. Okay, since then, the world was shocked to find that you can use these powers that now we have in our arsenal to factor large numbers. Now, depending on your taste and temperament, that may sound in varying degrees of extremely sexy or extremely boring. But Factoring large numbers is famously a difficult problem for classical computers to do. And the difficulty of it is the assumption on which cryptography is based, at least most forms of cryptography. HTTPS, the thing that secures all our traffic, is backed by the belief that finding the factors of a very large number would take a very long time to do, more time than any computer ever could do by the time the information is relevant. So encryption relies on this. In the early 90s, this fellow named Peter Shor came out of nowhere and surprised the world with a quantum algorithm that can factor large numbers in polynomial time. Ordinarily, factoring a number is an exponentially complicated operation in that the bigger the number is, the time it takes for a computer to do it grows exponentially. Add one more bit, now takes that many exponentially more flops for the computer to process the number. But now we can do it in polynomial time. This means doing something in minutes that would have taken hundreds of years, given a large enough quantum computer. So this is troubling and interesting and gives a sort of urgency to quantum computing. That algorithm really thrust quantum computing to the center stage for world actors because encryption is very important for security and communication. And the fact that quantum computers can, without exaggeration, break RSA encryption, the consequences of finally having a quantum computer are hard to predict what this is going to do for our world. There are encryption algorithms out there that can withstand the onslaught of quantum computers, just not the one that the internet uses right now. The good news is we have some time to figure this out. Right now, we're up to about 50 or so qubits on a given chip, and we'll need many thousands of qubits to efficiently do this factoring algorithm. All right, great question. Just to summarize, sorry I'm so long-winded. Those are the two main use cases: factoring, simulating. It is a very unusual state of the quantum world that we have so few algorithms. And the algorithms that we do have are so strange and so weird and don't bear any resemblance to classical algorithms, at least to my mind. Right now, we're in a period where it feels like algorithms are just discovered. That someone is going on a long walk or taking a shower, has this beatific vision, and an algorithm appears, something that we had no way of predicting that it could happen. They're very, very odd ducks, one to the next. Same thing with Grover's algorithm for performing a linear scan in logarithmic time. Who knew? And we don't really know what new algorithms are around the corner. It's just like digging in the earth, and occasionally you stumble across a nugget of gold. It's very much like that in the field right now. It's an active Wild West. Okay. So is it due to the exponentially higher information? Okay, so it is due to the exponentially higher information density. That's where the power comes from, yes. Does that additional work require exponentially more energy to run? Like if I had a qubit, do I need more power consumption? This is a really fun question. And it dips a little bit into information theory to answer. I have this Ralph Landau quote somewhere. Oh, must have been an entanglement. Oh, I really want to find it. It was Landau saying information is physical. The answer to the question is it takes, in principle, no more energy to add another qubit. And here's why. Energy consumption with your CPU, with computation in general, is directly correlated to erasing information. This guy Landauer, who kind of pioneered information science, we're getting off into the wonky weeds, but I'll finish this in a minute, discovered that the amount of physical energy it takes to do computation is related not to the amount of processing you're doing, but to the erasing that you do. When you erase a bit, when you erase information, that creates heat. Heat is hungry for energy. So the erasing is what causes energy to be consumed. It creates heat. None of our gates erase. If I take this qubit and I apply the gate here, did I lose any information? I say the qubit went from this state to this state. Did we lose information? Another way of putting that is, could you reverse the computation? Knowing the gate and knowing the output, could you deduce what the original state was? If you can't, then information was lost. Here's an example of a lossy operation. It's the OR gate. So I say I ORed 2 bits together and I got a 1. Now OR works by taking one, or if one or the other qubit is 1, then you get a 1. So I took 2 qubits, I got a 1. What were my 2 qubits? Well, you don't know. It could have been a 1-0, could have been a 0-1, it could have been a 1-1. That ORing operation loses information, generates heat, takes information. So it's a really great question, and it's a fun answer that qubit rotations, because they're not lossy, do not cost any energy at all. It's a perfectly free thing to do. If they did create heat, this is the fun fact that it would throw off what a qubit is. That these particles are so fundamental that all computation on them has to be at this level where there's no loss of information. Okay. I think those are all the questions. Let me go to the link page. I want to give up my screen. Give it back to the hosts. Actually, I'm going to go to the beginning because it has the link to the slides and my email address. Please feel free to write to me, and if you're curious about this in any way or have some lingering questions, I'd be more than happy to talk about it and recommend some books or articles or videos or courses. I truly believe that this quantum computing stuff, it's very simple, much like programming is very simple to get off the ground and start doing. And much like programming, if you've never done it before, it seems impossibly hard and arcane and complicated. But once you sit down and write Hello World for the first time, the feeling, at least I got, was that's it. That's all it is. And learning this is just more of the same. That's it with this presentation too. I tried not to hide any of the gory details with showing the linear algebra to get across that really is it. That's really all that's going on with quantum computing. And when you go and look at Shor's algorithm for factoring large numbers, it's not going to be any other principles that we've seen. You've seen all that there is to see of the fundamentals of working with quantum computing. And I think it's fun that we could do that in an hour and a half or 2 hours. And I want to thank everyone for taking time this evening to do this. And with that, Boyd, JJ,
Thank you, Thomas. Thanks, Thomas. That was amazing. I think we're going to end up looking back on this in 5 years as we're changing all of our passwords as something that cannot be unraveled by a quantum computer, and thinking you heard it there first. Truly amazing stuff. Again, as Thomas said, thanks for spending your Monday night with us. You can actually see this on YouTube. The link is in the Meetup. Let me mention the job board one more time. Laura's done a hell of a job putting all that together. And if you've got friends or whatever that want to see it again, there it is. Thanks to Paul and JJ for not crossing the streams, but getting it onto YouTube. Had to make the Ghostbuster reference. So with that, let's call it a night. Real quick, we will not be meeting at Rackspace until after August. Unfortunately, that's the word that we're getting from our rackers. So we're planning to continue to improve our way of meeting this way until such time as we hear otherwise. Thanks again, y'all. Have a great evening.
Thanks.